Welcome to the Deep Dive. We're the place where we take a whole stack of information, really dig in, and pull out the most fascinating insights for you. Today we're plunging into something really pivotal in the history of artificial intelligence. I mean, a shift so profound, it wasn't just a tweak, it fundamentally reshaped the entire field. We're exploring what researchers often call the statistical turn. Now, try to picture this. AI starts out, right, with these really rigid rule books. Think like a chess grandmaster, playing purely by memorized openings and responses. Every single move, every possibility had to be explicitly coded. But then the field sort of discovered, or maybe it's better to say fully embraced, the incredible power of probability and data, tons of messy data, and statistical inference. This wasn't just, a technical upgrade. It was deeper, a philosophical evolution, really. AI moved away from trying to explicitly know everything, like having a definitive set of facts, and instead embraced this constant dynamic process of predicting. It's a completely different way to look at intelligence itself, from a machine that knows what to do to one that, well, predicts what's most likely.
Right. And our mission today, really, is to unpack why this shift, this move from handcrafted rules, which were often quite brittle.
Yeah, fragile.
Exactly. To these more robust, data-driven statistics, why it mattered so much. We'll explore how it changed not just the algorithms, but the entire culture, the whole feel of AI research. It moved us away from needing exhaustive human expertise for every tiny detail, and instead it paved the way for the kinds of intelligent systems you use every single day.
Like chatbots.
Chatbots, yeah, or those amazing image generators that can create art from text prompts. You'll get a real nuts and bolts understanding, hopefully, of what's actually happening behind the screen. To really grasp why prediction became this new dominant paradigm.
And to help us navigate this, we've pulled together some really compelling sources. We've got insights from AI snake oil, prediction machines, the foundational text deep learning, Stuart Russell's human-compatible AI, and also some important historical perspectives on those early AI days.
All right, let's dive in and unpack this.
Okay.
The early days. Handcrafted rules and symbolic logic. The era of knowing. Okay, so to really get why this statistical turn was such a big deal, kind of need to start at the beginning, right? Where AI came from. In the very early days, the main vision for machine intelligence was almost entirely based on symbolic logic and explicit rules, hand-coded rules.
Yeah.
Think of it like a programmer having to feed the computer every single instruction, every possible scenario, every bit of knowledge, every logical step. It was painstaking, defining the world rule by rule.
Exactly. The dominant belief, really from the 50s through maybe the 80s, was that if we could just perfectly codify human knowledge, human reasoning, into this huge comprehensive set of logical rules, like a giant if-then instruction book for everything.
Right. Then computers could achieve intelligence. The whole approach was about AI knowing things, explicitly, declaratively, like here are the facts, here are the rules. Intelligence was seen as manipulating symbols according to those rules.
And a classic example, maybe the most famous one from that era, is Joseph Weissenbaum's Eliza. Built at MIT, mid-60s?
That's right.
And it was a chatbot. But crucially, no machine learning at all. Purely rules-based. It mimicked a psychotherapist, right? Reflecting things back.
It worked using really simple pattern matching. It looked for keywords in what the user typed, and then it had rules to transform that input into a kind of generic response, often a question.
Like if you said, I'm feeling down.
Yeah, it might say, why are you feeling down? Or tell me more about feeling down. Pretty simple stuff by today's standards, basically just turning your words back on you. But the impact back then was stunning. Weizenbaum himself, he observed what he called powerful delusional thinking in quite normal people.
Delusional thinking, wow.
Yeah, people would really ascribe understanding, even empathy, real feelings, to this simple program they'd get attached to it. Even after Weizenbaum explained exactly how it worked, just simple rules, folks. That tendency, that deep human need to project understanding onto machines, even simple ones, that became known as the Eliza Effect. It showed how much we want connection.
That's incredible. Just a few simple rules create this powerful illusion. But, okay, despite that early buzz, this symbolic logic approach, it started hitting some serious walls, didn't it?
It really did. While symbolic logic, these rule-based systems, they were brilliant at certain things, abstract, formal tasks, like chess.
Right, where the rules are totally defined.
Exactly. Completely defined, unambiguous, easy for a programmer to list out. Chess is a closed world, perfect for rules, but they really struggled with the real world. Its messiness, its uncertainty, its ambiguity.
It is kind of ironic, isn't it? The stuff that's super hard for us humans, like complex chess calculations way ahead.
Yeah. Mentally taxing.
That was relatively easy for these computers because the rules were clear. But then things that we do without even thinking, recognizing a face in a crowd, understanding someone mumbling in a noisy room.
Or just knowing that's a cat, even if it's half hidden or at a weird angle.
Right. Those everyday things were incredibly hard for early AI. They just couldn't handle it.
And that difficulty, a lot of it came down to things like the frame problem or the common sense problem. The basic issue was the real world just doesn't follow neat, exhaustive rules. Try writing a rule for every single way a cat might look in a picture. Different breeds, lighting, angles, partly blocked views. It just explodes into infinite possibilities.
A combinatorial explosion.
Yeah,
Right?
exactly. Or think about conversation. Sarcasm, irony, humor, what's not said. How do you write rules for all that? You can't. The rules would fail, they'd contradict each other, or they just wouldn't cover new situations. It became clear that knowing in this explicit, rule-based way just wasn't enough for real-world complexity.
So needing human experts to manually craft and constantly update rules for every single possibility, that just became this massive bottleneck, unsustainable. It made the systems really brittle, didn't it? They'd break easily outside their narrow little domain.
Totally brittle. And hard to scale. This led to that slowdown in the late 80s, early 90s, the so-called AI winter. Funding dried up, enthusiasm waned, largely because these symbolic systems just couldn't deliver on the bigger promises. It wasn't about processing power yet, it was the whole approach. 2. The groundwork for change. Embracing uncertainty, the shift begins, which brings us right to the turning point. The realization that sparked the statistical turn, dealing with uncertainty. It started dawning on researchers that, a truly intelligent system couldn't just live in this perfect, clean, logical world.
It needed to handle the messy stuff.
Exactly. Incomplete information, noisy signals, contradictions, ambiguity. Classical AI before the 80s often just assumed a fully observable, deterministic world, like everything was known and predictable.
Which is not life.
Yeah.
At all.
Right. Think about driving a car in traffic, or trying to understand someone on a bad phone connection, or just figuring things out when you don't have all the facts. Uncertainty is the norm.
Yeah, our sources point out that even modern machines stumble when they don't have enough data, or when something rare happens that's outside their training. Makes sense.
So this gap, this disconnect between the idealized AI world and messy reality, it led to this really critical insight. Maybe instead of trying to eliminate uncertainty with impossibly complex rules.
Which wasn't working anyway.
Right. Maybe AI should embrace uncertainty, use probability theory, quantify it, manage it, reason about it.
Okay, so shifting from trying to know for sure to figuring out the likelihood.
Precisely. A move from absolute knowing to probabilistic predicting. Estimating chances, understanding distributions, assigning degrees of belief instead of demanding certainty that just isn't there. That was the intellectual shift. That was the seed of the statistical turn.
And what's really cool is that the math for this, the tools, they weren't new. They'd been around for centuries.
Yeah, it's amazing. You've got figures like Pascal and Fermat laying the groundwork for probability back in the 1600s, figuring out gambling odds.
Figures?
And then Daniel Bernoulli later on with things like the law of large numbers. The mathematical toolkit was sort of waiting.
Waiting for AI to catch up?
In a way, yeah. And the key piece, the one that became really central, was Bayes' theorem. We see that referenced everywhere.
Reverend Thomas Bayes, right. 18th century.
That's the one. It gives you this formal, elegant way to update your beliefs when you get new evidence.
Can you break that down a bit? How does it work practically?
Okay, think simple. You start with a belief. Say, you think there's a 30% chance it'll rain today. That's your prior belief.
Got it.
Then you get new evidence. You look outside, see dark, heavy clouds rolling in. Bayes' theorem gives you a mathematical way to combine your prior belief, 30% chance, with the new evidence, dark clouds, to get an updated belief, a posterior probability. Maybe now you think it's, say, 70% likely to rain.
Okay, so it's a structured way to learn from new information.
Exactly. It's dynamic. It allows systems to learn from data as it comes in, rather than just follow static rules.
So the internal logic changes. Instead of if dark clouds then rain,
Which is too rigid, often wrong.
it becomes more like if dark clouds, then probability of rain increases to 80%. Based on past data linking dark clouds and rain.
Precisely. That's the huge shift. Moving from rigid certainty to informed likelihoods. Acknowledging uncertainty and having a mathematical way to handle it, that was the dawn. 3. The statistical turn takes hold. Data, probabilities, and machine learning.
Okay, so by the 90s, This theoretical shift towards probability starts showing up in actual AI systems. And we see the rise of machine learning, especially something called supervised learning. That became huge, right?
Absolutely. Supervised learning became the workhorse. So the concept is pretty intuitive, actually. You train an algorithm with a big pile of examples, and crucially, each example is already labeled with the correct answer.
Like digital flashcards.
Perfect analogy. If you want an AI to spot cats, you show it thousands of pictures labeled cat or not cat. The algorithm's job is to figure out the pattern, to create an internal model that matches the inputs to the correct labels. It keeps adjusting itself to minimize the difference between its guesses and the right answers in the training data. And often, there's this little twist, a penalty for making the model too complex.
Like Occam's razor. Keep it simple.
Kind of, yeah. It helps prevent the model from just memorizing the training data and encourages it to find the underlying simpler pattern if possible. It learns by example.
And a key piece of tech that made a big comeback around this time was artificial neural networks, inspired by the brain, right?
Yep. These computation structures have inputs, nodes, or neurons that process information and connections between them with adjustable weights or strengths. They learn by tweaking those weights.
Strengthening connections that lead to right answers, weakening ones that lead to errors.
Basically, yes. Early neural nets were quite simple, often just one layer of neurons between input and output. They couldn't learn very complex stuff. They were too shallow.
Okay.
The big breakthrough came in the 80s, really, with Geoffrey Hinton and others developing back-propagation.
Back-propagation. Sounds complex.
The concept is clever, though. It's an algorithm that lets you efficiently train deep neural networks nets with many layers stacked on top of each other. Essentially, when the network makes an error, backpropagation calculates how much each weight in the network contributed to that error, working backward from the output layer. Then it adjusts the weights accordingly.
So it distributes the blame, kinda?
That's a good way to put it. It allows the network to learn much more complex hierarchical patterns because information is processed through multiple layers. This was absolutely crucial for scaling them up.
And that leads us to deep learning, right?
Okay.
That term just means using these deep neural networks with backpropagation.
Pretty much. Deep learning became the shorthand. And it was a game changer because these deep nets could automatically learn relevant features from raw data.
What do you mean by features?
Like in an image, the first layer might learn to detect simple edges or corners. The next layer might combine those edges to detect shapes. The layer after that might combine shapes to detect parts of objects, like an eye or a wheel, and so on, building up complexity.
So it learns the important bits itself instead of a human having to tell it, look for edges, then shapes.
Exactly. It automated that really difficult, time-consuming feature engineering step. The learning shifted from the human designer to the algorithm and the data. A huge shift.
Okay, but for these deep learning models to really work their magic, they needed fuel. Lots and lots of fuel.
Data. Massive amounts of data, and that's what started becoming available in the 2000s. The digital explosion, the internet, and then monumental projects like ImageNet.
ImageNet, tell us about that. Spearheaded by folks like Olga Rusakowski and Jia Deng at Stanford.
Right. Launched around 2009, it was this huge effort to create a massive, organized database of images for research. Unprecedented scale. We're talking about 1 million images just for training, carefully labeled into something like 20,000 different categories, plus another 100,000 for testing. It was a public resource that just turbocharged computer vision research.
And they started a competition based on it, the ILS VRC.
Yes, the ImageNet Large-Scale Visual Recognition Challenge starting in 2010. Which AI could classify these images most accurately? Progress was steady for a couple of years.
And then 2012 happened, AlexNet.
Bingo! AlexNet, a deep convolutional neural network from Alex Krzhevsky, Eliza Effect, and Geoff Hinton's group at the University of Toronto. Their results just blew everyone away. A watershed moment.
How much better was it?
They achieved a 15.3% top 5 error rate. Now, top 5 error means the correct label wasn't in the model's top 5 guesses only 15.3% of the time.
So it got it right, or nearly right, almost 85% of the time.
Exactly. And the previous year's best was around 26.2% error, so a massive leap in accuracy. It wasn't just winning the competition, it was definitive proof. Proof that deep learning, powered by lots of data and modern GPUs, was the way forward. It totally changed the culture in AI. Suddenly, everyone realized you could take these massive data sets and just learn from them, instead of building brittle rule systems.
It showed that these previously hard problems, like really good image recognition, were actually solvable if you had enough data and the right statistical tools. The statistical turn in action, loud and clear. 4, the core mechanism, gradient descent and its impact.
Okay, so let's peek under the hood a bit more. At the heart of so much of this deep learning success, there's this one core algorithm that does a lot of the heavy lifting. It's called gradient descent.
Gradient descent sounds intimidating, but you said it's surprisingly simple.
The core idea is, yeah, basically every time the model makes a mistake on a training example, you tweak all those connection weights just a tiny bit in a direction that makes the mistake slightly smaller next time. Okay, like nudging it towards the right answer.
Exactly. It's iterative. You keep making these tiny adjustments over and over for millions or billions of examples.
I like the analogy you used earlier, hiking down a foggy mountain. You can't see the bottom, but you can feel the slope right where you are.
Right.
So you take a small step in the steepest downhill direction you can feel. Repeat, repeat, repeat.
That's it. The gradient is just that steepest downhill direction on the landscape of errors. You calculate it, take a small step down the gradient, adjust the weights, and do it again. These tiny iterative improvements are what allow the network to slowly learn incredibly complex patterns without needing explicit instructions.
And the amazing thing is, you're saying this same basic algorithm, gradient descent, is behind all sorts of different AI, chatbots, image generators, medical diagnosis, pretty much. The fundamental learning mechanism is often the same. What changes dramatically is the data you feed it massive amounts of text for a chatbot, images for an image generator, and the specific architecture of the neural network. You know, how the neurons are arranged in layers, the types of connections, but the engine driving the learning, often gradient descent or a variation of it.
That shift towards one general-purpose learning algorithm, instead of needing a unique, handcrafted approach for every single task, that must have totally changed how people did AI research.
Oh, massively. It was revolutionary for the culture. Developers didn't have to be niche experts in symbolic logic for, say, language and separate experts for vision. They didn't need to start from scratch designing a whole new algorithm for each problem.
That sounds incredibly empowering.
It was. It sort of democratized things. Researchers could focus more on getting good data, designing network architectures, tuning the training process, rather than trying to manually encode all human knowledge. Now, there was a trade-off, of course. These general models often need way more data to reach the same accuracy as a very specialized hand-built system might achieve on a narrow task.
They're data hungry.
Extremely data hungry. But because the culture had already shifted towards using and sharing massive data sets like ImageNet and compute power was increasing, that data requirement wasn't seen as a showstopper. It was an acceptable price for the incredible versatility.
It's just fascinating. This move from needing detailed knowing programmed in to systems that could learn directly from observation and then predict, it changed the whole game, technically and conceptually. The philosophical shift from knowing to predicting. So this technical change, this cultural shift, it really gets down to a deeper philosophical change, doesn't it? The move from AI trying to know facts and rules to AI that mostly predicts.
Absolutely. It's a fundamental rethinking of what we mean by intelligence in a machine.
And maybe even in ourselves.
Possibly. There are theorists, like Jeff Hawkins in his book on intelligence, who argue that prediction isn't just one thing the human brain does. It's the foundation of intelligence, the core function. His idea is that our brains, especially the neocortex, are constantly making low-level predictions about everything what we'll see next, hear next, feel next. Our whole reality is built on this constant stream of predictions being compared to actual sensory input.
Whoa. So our brains are essentially prediction machines.
That's the argument. And if that's true, then when we build machines that get really, really good at prediction...
They're tapping into something fundamental about intelligence itself, not just a clever shortcut.
Exactly. It suggests AI found a path that resonates, maybe, with our own biological intelligence. It elevates the statistical turn beyond just better engineering.
And you see this everywhere now. Modern AI is built on prediction. Chatbots predicting the next likely word.
Image generators predicting the right pixels to form a coherent image based on a prompt.
Systems classifying things, recognizing faces, recommending movies. It's all prediction based on past data patterns.
They don't know in the way we think of knowing facts. They infer probabilities. They find statistical correlations, often incredibly subtle ones, in the data, and use those to forecast or classify.
Even something complex like a self-driving car.
Fundamentally predictive. It's not following an infinitely complex rulebook for every possible situation. It's predicting. Predicting what a human driver would likely do, predicting the trajectories of other cars and pedestrians, based on vast amounts of training data showing those scenarios.
And that leads to that interesting idea you mentioned: as prediction gets cheaper and better,
the value of human judgment goes up. Defining the goals for the prediction, deciding what outcomes are desirable, interpreting the results, setting the ethical boundaries, that becomes even more crucial. We guide the prediction.
But this prediction paradigm, it's not perfect, right? There are challenges. Overfitting, for example.
Right, overfitting is a big one. That's when the model learns the training data too well, including all its noise and quirks.
Like memorizing the answers for the test instead of understanding the subject.
Exactly. It looks great on the data it trained on, but fails miserably when it sees new, slightly different data. It hasn't generalized. That polynomial example you mentioned earlier, drawing a super complex line that hits every single training point but completely misses the real underlying trend, that's overfitting.
And another huge issue is bias in the data itself, right? Like with ImageNet.
Yes, absolutely critical. If the data you train on reflects societal biases, historical inequalities, or just isn't representative of the real world, the AI will learn those biases and often amplify them.
Because it's just learning patterns from the data it's given.
Precisely. The ImageNet team's effort to remove thousands of problematic people categories because they contained harmful stereotypes or were just unfair, that shows how vital data quality and curation are. Data isn't neutral. It carries the baggage of the world it came from. Managing that is a constant struggle.
And then there's the black box problem. We know these systems make amazing predictions, but we don't always know why.
That's a huge challenge. The development of these complex deep learning models has kind of outpaced our ability to fully understand their internal reasoning. They can be inscrutable.
We see the input, we see the output, but the middle part.
It can be a mystery.
Yeah.
And that's not just intellectually unsatisfying. It's a real problem for trust and safety, especially in high-stakes areas like medicine or autonomous systems. There's a whole field now, interpretability or explainable AI, trying to develop techniques to crack open that black box and understand the how and why behind the predictions. Outro.
Okay, so wrapping this up, we've traced this journey from AI as this meticulous rule follower, trying to build intelligence from explicit logic.
And often struggling with the real world's complexity.
Right. To AI as this master of probability, learning from enormous data sets to become incredibly effective at prediction. The statistical turn shifted everything.
It moved us from trying to make machines know in that old, rigid sense to letting them learn patterns and predict using algorithms like gradient descent, fueled by data.
It changed what AI could do, how research was done, even how we think about intelligence itself.
For sure. But it also leaves us with this ongoing tension, doesn't it? The incredible power of prediction on one side.
And on the other, the need for good, clean, representative data, the ethical considerations, and the need for us to actually understand how these complex systems work.
Exactly. It's this constant interplay between the algorithms, the data they consume, and our human judgment and oversight.
So as AI keeps getting better at predicting our world, predicting our behavior, maybe even predicting human judgment, it leaves us with a big question, doesn't it? If prediction really is the foundation of intelligence, what does that mean for us? For how we value knowing versus predicting? Will our own definition of intelligence keep shifting as these machines evolve alongside us?
That's the question to ponder.
Keep asking those questions, keep digging deeper. We'll be back next time to explore another fascinating stack of information with you. Thanks for joining us on The Deep Dive.